Okay, great.
Yep. Okay, I think we should start. So hello, everyone. Welcome to the OC3 webinar of June. And today we are glad to have Madison Shankle from University of Andrews as our University of St. Andrews as our speaker. First, I would like to briefly introduce Maddie. Maddie got her bachelor degree in geology and geophysics from Yale University with a double major in environmental engineering. She was a Hui Summer Student Fellow during her undergraduate. Maddie was a research associate at Yale for 1 year and got her master's degree in physical oceanography from Bangor University before she moved to St. Andrews for her PhD studies. Her research interest is quite broad about paleoceanography, as she mentioned, Pliocene, ice ages, but she has a expertise in boron isotopes, as far as I know. She has published a nice paper in Nature on the Pliocene decoupling of equatorial Pacific temperature and pH gradients. And today her talk will give us more information about that. Okay, with that, I will pass the torch to Maddie. Thank you very much, Maddie, for giving a talk today.
Yeah, thank you for having me. Okay, yep, so as Ning said, I have very varied interests, but it's a little bit half proxy proxy data reconstruction and half working with model output. But generally what I'm interested in is understanding how the ocean flowed and operated under past climate states. So in my PhD here at St. Andrews, I study the ice ages and the role that the Southern Ocean played in drawing down atmospheric CO2. So I'm using boron isotopes to reconstruct deep ocean pH and carbon content to that end. But today I'm going to talk to you about an older period in Earth's history, the Pliocene, and I'm going to talk about what was going on with East Pacific upwelling under this past warm climate state. So as Ning said, this is a study that's been published in a paper now, and it is some work that I did while working at Yale University following my graduation. Okay, so I'll start with an overview of modern tropical Pacific climate. And one of its most important features, of course, is upwelling, or the rising of deep water from very deep depths up to the ocean's surface. So in the Pacific today, we have strong upwelling in the east, and it's this rising of cold, deep water that produces the East Pacific cold tongue in the east and the West Pacific warm pool in the west. So we have this strong east-west temperature gradient that's a very pervasive feature of the tropical Pacific. But of course, these dynamics are involved in El Nino dynamics. So as we dip into an El Nino event, we get a shutdown of that upwelling. And this allows all that warm water to slosh back across the basin, resulting in a typical El Nino type temperature pattern of warm temperatures across the basin, in contrast to the east-west hot-cold gradient we had before. So with this upwelling being collapsed, this not only shuts down nutrient delivery to the surface, where there's normally a highly productive marine ecosystem, but it also has wide-reaching implications for global climate as well. So El Nino dynamics are one of the most important modes of interannual climate variability, as they influence not only climate in the tropics, but climate farther abroad as well. Yet, despite the importance of these dynamics for climate and weather and marine ecosystems, and even human socioeconomic well-being, there still remains considerable uncertainty in how they will respond to future warming. So to that end, paleoclimate scientists like myself investigate this question by looking at past warm climates of the Earth, such as the Pliocene, and study these as analogues for how the climate will behave under future warming. So here I'm showing the global stack of the benthic oxygen isotope record. And this is basically just a global average of oxygen isotopes measured on deep sea dwelling foraminifera. And what it reflects is the joint influence of two things: the temperature of the global deep ocean and the deep water these foraminifera were living in, and also land ice sheet volume. So with these two things together, records like this have a pretty good finger on the pulse of Earth's climate. So you can see here the major swings of the more recent ice ages in Earth's history. And the Pliocene was this relatively warm period back here. So the Pliocene was a period spanning 5.3 to 2.6 million years ago. And it's significant for being the most recent time in Earth's history when CO2 levels were similar to those seen today, so around 300 to 450 ppm. Along the same lines, global temperatures were somewhere between 2 and 4 degrees warmer than pre-industrial, which again is comparable to temperatures we are expected to reach by the end of this century. So for these reasons, the Pliocene epoch is often studied as an analog for future warming, and paleoclimate scientists study its climate to gain insights into how Earth's climate might behave in the near future. And even besides these 2 points, there are many other things like vegetation cover and continental configuration and seaways that were largely similar in the Pliocene as they are today. So again, I think the Pliocene is becoming an increasingly popular period of climate history to study as an analog for future warming, as compared to perhaps older warm climate states deeper in Earth's history. However, despite being a very well-studied period of Earth's past, there are many features of the Pliocene climate that we still do not fully understand. And one of these involves East Pacific upwelling. And interestingly, there appears to be a paradox in that if you look at proxies for past ocean temperature and proxies for past ocean productivity, they seem to tell conflicting stories as to what was going on with Pacific upwelling. So if you first look at proxies for sea surface temperature, they indicate an El Nino-like temperature pattern persisting in the tropical Pacific during the Pliocene. So what I mean by that is, in contrast to the strong difference in temperature we see between the East and the West that we have today, we see a collapse of that temperature gradient and an overall reduced zonal temperature gradient as we go back in time, back into the Pliocene, with nearly equally warm temperatures in the East as in the West. And we see this in both proxy data, different types of proxy data, and also model simulations. We see that the East was anomalously warm relative to the West back in the Pliocene. So what we get is a reduction of this temperature gradient between the East and the West. So where today there's a difference of about 4 to 5 degrees Celsius, if you go back into the Pliocene, we see that gradient being as weak as 3 or even 1 degrees, depending on which proxy you're working with. So there is certainly some uncertainty in the magnitude of this gradient, but what I'll say is that all lines of evidence point towards it being reduced. And this, of course, is consistent with those El Nino-like dynamics of a shutdown of upwelling in the East, preventing that cold, deep water from coming up to the surface and allowing the warm temperatures to pervade everywhere across the basin. Okay, so temperature proxies suggest reduced Pacific upwelling. However, if we look at proxies for past ocean productivity, we actually see blooms and elevated productivity back in the Pliocene and Miocene in the East Pacific. So we see this in this record of barite fluxes, for example, but it's also seen in lots of other proxies for export production, such as opal and carbonate fluxes. So conventional wisdom would hold that elevated productivity typically reflects stronger upwelling, since it's the delivery of crucial nutrients from upwelling deep water up to the surface that fuels primary production. So these high levels of productivity suggest that upwelling in the East Pacific must have been maintained, if not even stronger during the Pliocene than it is today. So we seem to be at a bit of an impasse here with just these two lines of evidence, and there's lots of different proxies on both sides supporting them. And like I said, they're telling seemingly different stories about what East Pacific upwelling was doing during the Pliocene. So if we left it up to these two sets of proxies, temperature and productivity, the question might remain unresolved. But what I set out to do was revisit this question of Pliocene Pacific upwelling using a new proxy, the boron isotope pH proxy. And the idea was that deep water typically tends to be more acidic than surface waters due to the sinking and remineralization or breaking down of organic matter, which liberates CO2 into the water and makes it more acidic. So if the upwelling of deep water was enhanced or reduced in the Pliocene, we expected that we should see this manifested as a change in surface water pH. So we reconstructed records of surface pH from the modern back into the Pliocene using this proxy. And finally, we combined these proxy reconstructions of pH with new model analysis to diagnose specific physical changes in ocean circulation leading to these pH results. So, as I said, deeper water tends to be more acidic than surface waters due to the remineralization of carbon-rich organic matter. So remineralization is the process of tiny microbes breaking down dead organic matter that's constantly sinking through the water column. And this liberates constituent nutrients and carbon in that organic matter back into the water column. So because this is constantly happening, the carbon content of water tends to increase with depth the deeper down you go. So deeper water tends to be more acidic than surface waters. And with this logic, we believed we could investigate equatorial Pacific upwelling during the Pliocene by producing two records of surface pH, one for the East Pacific and one for the West. And then if we saw a relatively more or less acidic signal in the East than the West compared to modern, we believed that this could be evidence of acidic carbon-rich water reaching the surface or not, and thus be a measure of the strength of upwelling back in time, at least qualitatively. So to make these records of pH, I used the boron isotope pH proxy. And the way this proxy works is that there's a pH-dependent speciation of boron between the two predominant species found in seawater. So at very, very low pH values, we would expect 100% of all the boron existing in the ocean to exist in the form of boric acid in the red curve. However, as you move to higher and higher pH values, proportionally more and more of your boron will exist in the form of the borate ion in blue. So as the acidity of the water changes, so does the amount of each of these two species of boron. And this just comes about from the acid-base equilibrium reaction between boric acid and the borate ion. So under more acidic circumstances, with more hydrogen ions being around, that's going to push this equilibrium reaction more to the left, and you'll get more boron existing in the form of boric acid. And vice versa, under less acidic conditions, with fewer hydrogen ions around, it pulls the equilibrium to the right, and you have proportionally more of your boron tending to exist in the form of borate ion. So this pH-dependent speciation of boron then necessarily leads to a pH-dependent fractionation of boron isotopes between these two species. So if you think about it, the ocean never loses or gains boron except on very long geological timescales over millions of years. So if it never loses or gains boron, its overall boron isotopic composition of the ocean must be staying the same. And in fact, for the modern day and recent time, that value for seawater is about 39 per mil for our purposes and on short timescales. So if you have the amount of each of these molecules varying with pH, each of their delta 11b values must also change with pH, such that the boric acid of this delta 11b value and this amount of borate ion of this delta 11b value, when you combine that together, it's always going to give the overall delta 11b of seawater. So to put it more concisely, just know that there's a predictable relationship of how the delta 11b of each of these two species changes with pH in the ocean. And then this gives us a way of reconstructing ocean pH back in time, since when the borate ion gets incorporated into biogenic carbonates, such as the calcite tests of foraminifera, it takes with it this pH-determined delta 11b value. And thus we have a measurable way of estimating the pH of the ancient seawater in which these forams grew. So in my study, I measured boron isotopes on Orbulina universa, which is a surface-dwelling species of foraminifera. So its boron isotopes will be reflecting surface water pH. And like I said, I produced 2 records of pH back in time, one from the Eastern Equatorial Pacific and one from the West. And here are those records. So the blue data points show data from the East Pacific, and the red data points are from the West. And within each cluster of dots, the thick point is the average of the 4 that you see around it. So in the top panel, I show the raw boron isotopic values of my samples with analytical uncertainty given in the error bars. And then the bottom panel shows the pH that I calculated from those boron values using a species-specific calibration for pH and showing 2 standard deviations of uncertainty from a Monte Carlo simulation that I did for the pH calculation. So what we record is an overall reduction in pH going back into the Pliocene, so more acidic waters. And this is simply reflecting the elevated CO2 levels of the Pliocene. So for example, if we take the Western equatorial points, which is a region of the ocean understood to be in equilibrium with the atmosphere, so its pH will primarily be driven by changing atmospheric CO2 levels. We record pH in the West Pacific dropping from a modern value of about 8.07. And these modern values are just taken from an average of cruise-based observations. But we record a drop in pH back into the Pliocene from 8.07 to about 8.02. And this pH value of 8.02, if you do some calculations involving carbonate chemistry, corresponds to an estimated atmospheric CO2 value of about 439 ppm, which is well in line with previous estimates of Pliocene CO2 levels. So that's excellent. But now, looking at the East Pacific, we see that there's also a reduction in pH, but you can see that it is a larger reduction, widening this gap between the East and the West. So in contrast to the West, we see a larger drop in pH in the East of about 0.13 units. And yes, these pH values and these changes seem quite small, but in fact, when taken together, their cumulative effect is quite important because in fact, what we find is that the zonal pH gradient between the East and the West becomes enhanced in the Pliocene, being more than double of that of the average modern gradient. And that's the important part. And again, it's because of these relatively more acidic conditions coming about in the East, beyond what's predicted from just higher CO2 levels. So the question then becomes, why these extremely acidic conditions in the East? And of course, we can say that acidic conditions could come about from the enhanced upwelling of acidic deep water. But of course, you can't diagnose a mechanism so specifically as that with proxy data alone. So it was at this point that we turned to model output to supplement this data and to see what was going on in ocean circulation to produce such acidic conditions in the East. So what I'm showing here is a map of pH from the model output with my data from the Pliocene overlain as dots. And our collaborators who we worked with used the CESM model version 1.0.4, which is a coupled ocean atmosphere climate model with active biogeochemical cycling. And it's also a model that has been used in other past studies of the Pliocene climate. So if you're familiar with these studies by Burles et al., you might remember that in these model runs, certain modifications were made to cloud albedo properties. So cloud albedo was reduced in the extratropics and increased in the tropics. And these modifications are done because they are found to more accurately reproduce sea surface temperature gradients. And it's these temperature gradients that are so important for correctly simulating ocean circulation. So that's just a little disclaimer. We're aware that that's not necessarily physical, these cloud albedo changes, but if we limit our analysis to just ocean circulation, we have confidence that we're simulating the Pliocene Ocean correctly. And this figure is meant to provide evidence of that. So here, this map shows pH across the surface of the Pacific Basin as produced by a Pliocene-like run of the model. So we have the equator here, and we have Indonesia here in the west, and this is the west coast of South America here in the east. And this figure is just meant to demonstrate the nice agreement we see between the model output and pH as reconstructed by proxy data. So in the West Pacific model, the model gives pH values between about 8 and 8.05, which matches the data nicely. And similarly in the East Pacific, model pH ranges from about 7.85 to 7.9, which again is in excellent agreement with our data points. So this figure is just meant to demonstrate that the model appears to be working well and is reproducing major features of the Pliocene Ocean as evinced by the proxy data. And this in turn gives us confidence to really dive deeper into the model output and pick apart what is going on. So this is why I like working with data and models together. They work together really nicely, I think. On the one hand, we need this proxy data to validate this kind of crazy model that we're using. But on the other hand, the model was able to provide more information around the data. And as we'll see on the next slide, even a mechanism by which these acidic eastern conditions could have come about. So further analysis of the model output suggests that the enhanced acidity of the Pliocene East Pacific can be explained by essentially a large-scale reorganization of Pacific climate, or Pacific circulation, rather. So what's more, we find that this reorganization involves both deep water formation in the North Pacific and an active meridional overturning circulation, both of which are notably absent from the Pacific today. So I'll walk through our evidence we have for this now. And what I'll be showing are north-south transects averaged zonally across the Pacific Basin for values of different variables. And where anomalies are shown, they are anomalies of the Pliocene-like run of the model minus a pre-industrial control run of the model. So first, again, this is latitude along the x-axis and depth along the y-axis. And just notice that we've truncated the axis a bit to be able to show surface waters and deep waters. So here what we see is the pH anomaly of the Pliocene run relative to the pre-industrial run. And what we see is relatively less acidic, higher pH water coming down in the North Pacific, coming down to depth, and eventually evolving into more acidic, lower pH waters as they travel south. And we see this signal reaching down to depths of about 1,000 to 2,000 meters. Next, in a similar fashion, we also see ventilation age evolving in much the same way. And by ventilation age, I just mean how long it's been since this water has been at the surface. And again, this is an anomaly. So this is actually our first evidence of deep water formation in the North Pacific, because what we're seeing is relatively younger water, younger aged water coming down from the surface in the north, suggesting that this water has come down from the surface more rapidly than what we see in the modern. However, again, much like the pH output, the water evolves and ages as it spreads south and the longer it spends at depth. As it travels south to the Pacific, similar to how the pH evolves, become increasingly more acidic as we go along. And what we see is that ultimately, this increasingly older, increasingly more acidic water eventually comes up in the equatorial Pacific, and it's brought up by means of a basin-wide pathway, which is shown by the stream function here. So here, positive green values show where circulation is going in a clockwise motion, and the negative pink values show counterclockwise motion. And what you can see is how this forms a basin-wide overturning in which water travels down in the North Pacific, travels southward at depths of about 1,000 meters or more, crosses the equator, And eventually this relatively lower pH, older water comes up in the equatorial Pacific. And the final panel I'll show you provides further evidence of this circulation pathway. So what I'm showing here comes from a Lagrangian particle pathways analysis in which tracers were seeded in the North Pacific and allowed to flow forward in time. So this analysis illustrates in the darker colors the pathways that a majority of those particles took. So we can see that large numbers of these particles were taken down in the North Pacific, traveled down to depth, traveled southward again at about 1,000 meters or so, before finally upwelling very strongly in the equatorial Pacific. And even more importantly, from this analysis, we can calculate that it takes this water on the order of 800 years or more to travel along this pathway at depth. And this is in stark contrast to the modern, in which most of the water upwelling in the East Pacific comes from the nearby subtropical cells, which you can see here. But in these cells, it only takes on the order of tens of years to reach the equatorial Pacific, and it doesn't travel nearly so deep, nor for so long to reach the equator. So if these results are accurate, they represent a very different Pacific than what we know today, and a very different circulation. And at this point, we're also approaching the point where we have a potential solution to our Pliocene paradox of how we could have warmer eastern temperatures indicative of reduced upwelling of cold deep water, but also strong productivity indicative of enhanced upwelling of deep water. So the potential solution we propose is that if we see older, more acidic water upwelling in the East Pacific during the Pliocene than in the modern, we presume that this water would also have contained more nutrients simply from spending such a prolonged time at depth and accumulating these nutrients over time through the ongoing process of remineralization. So by the time it upwells, it would have contained more nutrients than it does in the modern. And as I said, this in turn could explain these apparently conflicting lines of evidence. So even if there was reduced upwelling, allowing the East Pacific to achieve these warm temperatures that it did, if the water being upwelled itself was older from this longer, different pathway taken at depth, we presume this water would also have been more nutrient rich from the process of remineralization. And these nutrients could have supported the enhanced productivity that we also have evidence for, even if the upwelling itself was reduced. So in conclusion, we present a potential solution to the Pliocene paradox of having warm temperatures in the east indicative of reduced upwelling, but still high productivity indicative of strong upwelling and nutrient supply. So firstly, we provide proxy evidence of an enhanced zonal pH gradient in the Pliocene relative to the modern, largely coming about from a large drop in pH in the East Pacific. Secondly, model output attributes these acidic eastern conditions to a meridional overturning circulation during the Pliocene that allowed older, deeper, and more acidic waters to upwell in the East Pacific than currently do in the modern. These results are also significant for providing a new, fresh, independent line of evidence for Pacific meridional overturning circulation, which so far has been hypothesized and seen in some model output, but really direct proxy evidence has been probably lacking. So in terms of future directions, I would definitely like to see these records filled out with more boron data points. But I would also call on paleoclimatologists and paleoceanographers to look for other proxy data that's a bit easier to gather to provide more evidence of a PMOC and perhaps to quantify the nutrient content of this water that we're hypothesizing about. I could also stand to see this study could stand to be recreated with, I think, newer models perhaps, especially to see if we can recreate these results without the cloud albedo modifications I mentioned. And finally, I hope this study has just been a nice example of, like I said, proxy data and model output working together to paint a fuller picture of past climates. And I also hope it's been an interesting example of how you can use the carbon content of water and pH and chemistry to actually answer circulatory questions and understand how the ocean operated under a past warm climate state. So thanks very much for listening, and a big thank you to all of my co-authors, and I'd be happy to take any questions. Thank you.
Okay, great. Thank you very much, Maddie. That's a very fantastic talk.
Thank you.
Does anyone have any questions for Maddie? Yeah, please, Andreas.
Hi, Maddie. Nice presentation.
Thank you.
I have a question about the deep water formation in the North Pacific. Since, this is OC3 and we're concerned with carbon isotope data, I was wondering, is there any like C13 data from the Pliocene deep ocean that would support such a quite different circulation pattern from the one that we have today, or any other proxy from the deep ocean?
I'm sure there is carbon isotope data for that. And that's the exact kind of proxy I've been racking my brain about what else could we use to look at this question. It's unfortunate that I've moved on to a different period of Earth's history in my PhD. So I don't know the exact answer to that, but it's a very good question. And yeah, carbon isotopes probably definitely have the potential to look at this more closely. And I probably should have looked into them before giving this talk.
Maybe an incentive to expand our OC3 database into the Pliocene.
Okay, Maddie, I have a quick question. So I've read something about the role of tropical cyclones in modifying Pliocene upper ocean stratification, and also maybe even the zonal gradient along the equator during the Pliocene. Are you aware of any? I'm just curious because your co-authors, some of your co-authors were the people who proposed for the tropical cyclone hypothesis that can explain the kind of to reconcile the different observations during the Pliocene. I was wondering, how is this consistent with what you observed in this study? Stronger tropical cyclones.
Right, stronger tropical cyclones in the Pliocene because it was warmer and sea surface temperatures were warmer.
Yeah.
I have heard of this, and so the idea, right, is that with more or stronger cyclones, that would weaken the stratification and that would allow more nutrients to come up.
I mean, I'm not an expert in my understanding is that there's no tropical cyclones along the equator. So it only plays a role a little bit off the equator when the water moves from the high latitude towards the equator, that it can mix the upper ocean with, the water below the thermocline. And that would change the pH of the water, I assume. But I'm just curious whether the hypothesis that, for example, I think Alexei and I forgot the other author's name. So they had maybe two papers in Nature, like in 2011, and they used stronger tropical cyclone to explain lots of phenomenon during the Pliocene. I was wondering, could that also explain what you observed? Yeah, it's kind of a open question, but
yeah, no, it's a good question. I mean, the thing that I know best is pH in the upper ocean of the Pacific, because that's what I was working on. And depending on how deep a cyclone can mix, I mean, it would have to mix deeper than the upper mixed layer because pH is constant through that. So I'm not sure if a cyclone could explain more acidic conditions. The only other thing I was going to say about stratification was that if cyclones could mix strongly enough to reduce stratification, and that could explain more nutrient delivery. I thought the bigger issue would be thermal stratification. and enhanced thermal stratification during a warm period of Earth's history. So even if the cyclones were going on, I don't know how much that would counteract the thermal stratification of a warmer climate. But I see another person with their hand up, so maybe they have some thoughts as well.
Oh, yeah,
different question.
Yeah, please, you can unmute yourself.
Yeah. Sorry, no, my question is sort of completely different to that.
Well, that was the end of my answer anyway. Sorry, Ning.
No problem.
But my question was just about sort of, you have this sort of highly acidic water that sort of upwells from the deep, and I was sort of wondering if there are any thoughts as to what process is making that water essentially come up from the deep, because the deep water has always been more acidic than the surface water. So what is it all of a sudden that pushes it up?
That's a good question. Without having gone into it very deeply, we attributed it to a weaker stratification, or I just talked about thermal stratification being stronger, but I think lower thermocline, if that water was warmer, it would have weakened stratification and been more in line with the waters above it. So more mid depths or like lower thermocline, weaker stratification from the water being warmer perhaps as well. But that was a bit of a hypothesized attribution at the end of the paper. I think that's more something that could definitely be looked at, especially physically on the physical side of things, not with proxies, but model experiments and everything. That's definitely something that could be looked at in a future study. A very good question. Thank you.
Okay.
And I think I thought of one last thing related to that. This was coming about from questions people were proposing about wherever this water is coming from, even if it's the North Pacific, perhaps that water would have been warmer because it's the Pliocene and temperatures were warmer everywhere. Surface temperatures were warmer everywhere. So perhaps it's just relatively warm water coming down and eventually upwelling that explains the warm east temperatures as well. So we took that and said, well, maybe if warmer water is getting injected, it could have reduced stratification, not such a hot, cold temperature gradient, making the mixed layer in the thermocline, but weakening the thermocline a little bit, if that makes sense, if I remember correctly.
I mean, because of the polar amplification during the Pliocene, that's very likely, in my opinion, that you have a warmer water upwelled. Is that true? Okay, I think Andreas has raised his hand. Yeah, Andreas.
I was just wondering if you have looked in the model results at productivity, export production, or something like that to compare with this, the barite or the productivity proxies that you've mentioned.
No, and it's too bad that I don't study this anymore. But if I had free time, I definitely would. Like, that's the exact kind of studies I want to see done, and I would like more evidence than just what we've thrown together. It was a lot of good work from everybody in this paper, but we looked at a handful of variables, and we could definitely stand to look at more.
Thank you.
Thank you.
Yeah, are there more questions? If not, I think if later on, if you have questions, you can email Maddie, and here's her email address. And also, her talk will be recorded and then posted on YouTube, then that you can check. I think usually I won't send the email to the people who attend the seminar, but next time for the advertisement, I will also send the link for the YouTube so that people who miss the talk can watch the talk. Yeah. Anyway, thank you very much, Maddie, again, and thank you everyone for attending the webinar. And our next webinar will be on July the 19th. The speaker will be Professor Loren Lisacki from the University of California, Santa Barbara. Okay, thank you again, everyone. I will see you next time.
Thank you very much.
Thank you, Maddie. See you. Thank you, Basil, for recording the talk.
Yeah, I've successfully done that, so I'll send that to Sarah. Okay.
Great. Thanks.
Thanks, everyone.
See you.
Thank
Yeah.
you.